pleasure for me to introduce Professor Clark Still. Professor Still received his bachelor's degree at Emory University in 1972 and his PhD at Emory with Professor David Goldsmith in 1973. After postdoctoral work at Princeton with Professor Todd Whipke, he was a postdoctoral fellow with Gilbert Stork from 1975 to 1976. He began his independent academic career at Vanderbilt in 1976, but returned here to Columbia in 1977 to join the faculty of the chemistry department. Here at Columbia, Professor Still made significant contributions to the field of organic chemistry, particularly in the area of natural product synthesis, reaction development, conformational analysis, macrocyclic stereo control, and computational chemistry. Still developed the integrated software program Macro Model in 1986 in association with Columbia University. Macro Model was acquired by Schrodinger in 1998 and is now offered as a full-featured program for molecular modeling. Professor Still also developed methods for synthesizing chemical libraries and resin beads using molecular tags. It became the foundation for the premier combinatorial chemistry company, Pharmacopoeia, which he co-founded in the early 1990s. Professor Still retired in 1998 as Distinguished Professor at Columbia. And Professor Still co-organized the Stork Symposium here at Columbia in 1992. It's great to have you back here today.
You forgot my greatest contribution.
Uh-oh.
Flash chromatography.
I didn't forget it, Clark. It was on version 1 and had to shorten it. Yeah, so I apologize for that. That was the short version. Okay. I've used it many times.
Okay, I was directed to say some things, not so much about my remembrances of Gilbert, but what I thought was great about his science and what he did for, in a way, all of chemistry and certainly for all of us. I'd like to roll back to the times when he first got started, when he was an undergraduate at the University of Florida. He was interested in quinine because it was the end of World War II. There were problems getting quinine, and he had also learned that one can make natural products in the laboratory, the same ones that nature makes. So while he was there as an undergraduate, he wrote a research proposal. You can see part of it down here. 20 pages of detailed analysis, hand-drawn structures, everything typed, 70 literature references on how to make quinine. I think he even tried to start in the lab. Didn't exactly work out, but he moved ahead, and in fact, eventually it did. Hold on. Which way? When he was a graduate student, I'm not really sure what his project was, but I think he did some submarine work also directed toward quinine. And one was to make this fairly simple compound here with the two cis attachments on the piperidine ring. In those days, as I show up here at the top, according to Stork, people really didn't pay much attention, this is in the 40s, to how to control stereochemical control. So he did this as a model reaction, which he published. You'll notice his name is first, McIlvaine's name is second, to show that you can make something which is a part of it. And it's shown over here in the white part. If you take that starred atom, yes, this starred atom, that, and cyclize nitrogen from that and makes this ring. So in any case, he stayed interested in quinine, as we will see a little bit more later. Okay? So as has been pointed out, Stork was very concerned with stereochemistry and how to make molecules with just the stereoisomer that people wanted or that was needed in nature. But it wasn't so easy. Not many people worried too much about it or really knew what to do. He shows a very simple compound as an example. It's cantharidin, and he made it by a couple of Diels-Alder reactions, and it specifically produced only the right stereoisomer. Admittedly, this is I guess it's probably, I assume it's DL, but it gives only the cantharidin structure. Obviously hard to get much more than this because it's pretty strange. This was the first example of a synthesis, stereospecific synthesis designed of a natural product. Should also, he noted later, Stork, as you see down here, that Surratt work, almost just a year later, the first stereoselective synthesis of a complex natural product that is cortisone. After that, he started becoming interested in how it is that nature makes some of the compounds. And in particular, he studied work by Lindstedt in the 30s. He found out that there was stereoselectivity involved in cyclization of 1,5-diene. In connection with work by both in his lab and also with Eschenmoser, they came up with a concept called the Stork-Eschenmoser hypothesis, that there is a stereospecific anti-parallel addition of carbidimines to an alkene. And then that was followed later on, as everyone knows, for making polyenes into steroids, terpenes, many other things, which turned out in the end to be very efficient. There's a long time between this, 1950s, and 1994. About the same time, Stork at Columbia with Bergstaller made some proposals about how one can get things like tricycloterpenes and steroids from squalene. And this is just a picture from one of his papers from 1995. You may see this as luteal as a terpene example, or cholesterol or aldosterol down here as a steroid example. Now, this is an interesting structure. I've seen pictures of cedrine and cedrol all around the place. In fact, there was some out in front. Didn't realize it, but it turns out that Stork and Breslow proposed the structure of cedrol. They didn't really know much about it, but they had a connectivity. They didn't really have a stereochemical proposal. So the proposal was in the journal for about a year, journals, and then Stork and Hill in Stork and Clark in 1955 did a total synthesis of both of these things, and in doing that established that the structures that were proposed by Breslow and Stork were correct, but also what the stereochemistry of cedrol and cedrine were. Later on, he went back to other things like alkaloids, total synthesis of allo-yohimbine, and then later on, as I say, 15 years later, he made yohimbine itself, which is this molecule. Among the natural products work that he did in the 60s were a number of alkaloids and also things like steroids down here at the bottom. Particularly, Stork tended to have a method that he was really interested in. Generally a new method, and that method would be used to create one or maybe lots of different examples with the same methodology. So these are just a couple of examples of fairly complex alkaloids. And then this one was interesting because he used the so-called isoxazole amylation method, where this moiety, which is a kind of a masked 1,3-diketone, could be used and opened up and put together to make large polycyclic systems like you see here for progesterone. One of the things which I think was for a long time the hallmark of Gilbert's work was the fact that he liked to create stereochemistry from an alpha-beta unsaturated carbonyl system. And he found out that lithium and ammonia makes transfusions. And that leaves a specific enolate which one can add something to. Propane, you can get this, you can add an electrophile, and probably get stereochemical control here as well. Or you could trap the enolate as a silyl ether. There are a lot of examples of this in his work. This is the one where he talked mainly about silyl ethers, and in fact this was the first use of the dimethyl silyl protecting group, at least for enolate. And then later on, we'll discover that you could get other stereochemistries with fusions, lithium ammonia, normally transfusions. Anyway, this methodology had a lot going for it because you could put in something at the back, either a hydrogen or an alkyl group, then get an enolate and put in something next to it for forming more damages on the grid system. There's a question I keep running into. It relates to dimethyl chlorosilyl protecting group. And there was a statement which said that the dimethyl protecting group, cytoprotecting, was introduced to organic chemistry by Stork. And it was alleged to be in a paper by Ian Fleming. I couldn't find that paper. Ian Fleming has a pretty long publication list, what a surprise. So I sent him an email, and he responded and said, yes, it's been a very long time, nice to see you. And in fact, yes, I did say that, and this is the reference. And so this is one of them. And this is exactly what Ian Fleming said. Ian Fleming. I had a neighbor who is called Ian, and I'm very confused, so I'm using these interviews. In any case, according to Fleming, Stork definitely was the one who introduced the T-butyl dimethylsilyl protecting group to organic chemistry, but of course it was terribly important that it could be used for alcohols, as Corey found out, and that you could remove it with fluoride ion without affecting other functional groups. Now here's an example of using this kind of technology where you do something like a lithium ammonia reduction, track with another thing, and it was used to make this compound, this pentacyclic terpene, luteal. First reactions put a cyclopropane in here. That can also be reduced by lithium and ammonia. You cleave that bond, that leaves the methyl group right here, axial, opposite to that, and leaves you an enolate that you can add something to, like methyl iodide. So this group of things, those two substituents were essentially put in by this lithium ammonia reduction to generate an enolate and trap. It gets used here again. I'm not going through the details. Used here again to put the hydrogen in. That's the normal trans fusion, and then trap it with allyl bromide. That's this. This then becomes that part over here, and it's done yet a third time. So the same methodology used over and over to generate pretty complex natural product. Very high severity chemical control. It was also used to make prostaglandins. There was a time in the 70s when prostaglandins, as we all remember, were very popular to make. Gilbert did a number of these things. One of the neatest ones, I thought, was the one down here. It starts with diglyceraldehyde to get that chiral center. There's then a Michael reaction where you add an enolate or add the cuprate of this to give the beta substituted carbonyl compound. This ends up on the more stable side, which is opposite from that on the 500 ring. The interesting thing is because Stork was associated with Syntex at times and knew some people there like Carl Bunch, he knew there was a way to take a cis olefin, the wrong stereochemistry, and convert that to a trans olefin with the right stereochemistry. So it even turned out that in this particular case, if you made a cuprate out of this, even if it's not stereo control, it's just racemic, only one of them really reacts well. And that's the one that gives the right stereochemistry for prostaglandin, E1. Now this is just a couple of papers. I don't really am going over my time here, but this is just a couple of papers which I think is spectacular. Scott Ignatsky, is he here today? Oh, yes. You're obviously going to remember this. Developed a method, and there's a two-paper back-to-back Jack's communication set. One in which he shows that you can take all the possible biosteriors of this little butylamide, and that they can then be put together to extend it to make a new butylamide, and then do it over and over. And that basically was done by Ignatsky in the second Jack's communication to make the erythromycin ring system. For one person doing all of this all by himself, except for Gilbert, who is not known for working well in the lab, pretty amazing. I thought this was spectacular. He also did a lot of free radical cyclizations. I'm not going to spend a lot of time here because I am running over, but just to point out, free radical cyclizations were not really used that much in chemistry, but Stork found out you could do things like you kick off a free radical cyclization here. That adds to the triple bond, leaves a free radical there, and that adds to here. So all of these rings are zipped up by one free radical cyclization. Another one is here. In the conversion of the cyclopentenyl derivative to prostaglandin F2 alpha. We also use the same idea to make delsamine. I'm just going to divide. The point is, he really creates reactions that other people didn't use very much or know much about. Find out what they can do and then use them over and over. And the neat thing about these free radical cyclizations is many times you can make several rings in one go. Finally, the Germany, his last project, huge amount of work. It was going on for many years, but Ayako Yamashita obviously had to make the whole thing work, do the finished part, and have to go through the whole synthesis herself to get enough material. The neat thing is that one chiral center, unlike getting lots of chiral centers from the chiral pool, that one chiral center controls the formation of 15 muons. That is an unbelievable, amazing thing. Unfortunately, by the time they got to the end, were running out of material, the compound they had an extra methylene right there. This really ought to be an OH. So there is a statement by Stork, you can see it down here, where it explains why exactly it is he didn't finish and get rid of that extending formula. Could have done it if he had more time. In any case, I just want to show one more slide and thank the people who have helped me. Ayako told me a lot about the German work. I've known her for many years. Ryan Fleming helped clarify the issue about dimethylbutylsilane cuprate. And I believe this man, Noah Burns, I think he was an undergraduate here. And he worked with Jim Lake, yeah, exactly right. In any case, he wrote a wonderful review. This is worth looking at. It's a review of Gilbert's career. Got lots of structures. I took a lot of material from that. Anyway, it's a spectacular work. He's now at Stanford and understands it very well. Thank you. Thank you very much.